Okay, I think, Kate, do you have a few things you would like to share with us?
Yes. So I am Kate Brunner. I'm the program manager for Standards Oversight Council, Penny referred to as SOC lovingly, for this technical standard 1010 proprietary filtration devices. DNR used the SOC process to collaborate with this broad team of stakeholders. I helped facilitate the process, and Eric Rortvedt, who you're going to hear from today, was the team leader. We had a team of, I think it was 13 people that met regularly. It took us over a year to discuss and refine and respond to the comments and respond to comments again. So hopefully you like what you see here. If you want to stay informed about things like team formation for future technical standards or updates to existing standards, public comment periods or training opportunities like this one, please sign up for the SOC listserv. We maintain a separate listserv for urban technical standards. It's not GovDelivery, it is a private listserv. It's still only 1 to 2 emails a month, so I try not to spam you, but you can obviously unsubscribe if you'd like. I'll post the link for where to sign up in the chat box. As Penny said, it was also in that kind of lengthy intro email with the link to this webinar, but you can subscribe by clicking the link in the chat box. Back to Penny. I think you're going to introduce Eric here.
Yes, great. Thanks so much, Kate. And
Thanks,
Kate, for all your help in getting this organized with Eric. And so I am very happy to have Eric Rortvedt today as our presenter. And I'm just going to tell you a little bit about him. Eric has a civil and environmental engineering degree from UW-Madison and is a professional engineer in Wisconsin. He has worked for the DNR since 1992, including over 20 years in the stormwater program. Eric is stationed in Fitchburg as a plan review engineer for the DNR South Central region and has a leading role in development of statewide guidance. Okay, so again, I'm just going to remind you, keep yourself muted and your webcams off. We find that helps with the bandwidth, and Eric will have his on during his presentation so you know who is speaking, and if he has problems with his bandwidth, he may turn his webcam off as well. That's up to Eric. We'll decide about that in a little bit. So Eric, are you ready?
Yes, can you hear me fine?
I can. Take it away.
Okay, here we go. Well, hello everyone. As is indicated, this presentation is on proprietary filter devices. This standard was just finalized a little over a month ago, and I was the team lead on this standard. Oops. Okay. As Kate mentioned, as far as the SOC Council, this is a process that many state agencies are using to have a uniform process to develop statewide standards. We pulled together a team, it was close to a year ago when we started on this particular standard. Being how this is a DNR standard, DNR is considered this custodian for it. We are for any of the erosion control or stormwater management technical standards, but there is a number of other agencies that use this, DADCAP, NRCS, Wisconsin Land+Water, and UW Extension. As far as the team that we had, typically there are somewhere in the range of maybe 8 to a dozen people that are on a SOC team. Kate was the coordinator. I was the team lead. Along with that, we basically solicit statewide for applicants that want to be on this type of team. And from here, we try to pick a diverse group of experts that are knowledgeable on the standard that we're looking to develop. So on this, we have a few representatives from manufacturers or those selling these devices, as long with private consultants that have used or are looking to use these devices into the future. As well, we even have some representation of those that have worked on models to model these devices. Okay, proprietary filtration device. You'll see the acronym PFD in this presentation a number of times. So what is a PFD? Generally, it's a granular media filter it could be a membrane by which water passes through to remove pollutants. Now, this standard was developed to basically come up with how to size or determine what efficiency is given for an actual PFD device. And when I say device, I'm not just saying the media that's used. It's actually, we're looking at the results of the chamber, the filter cartridges. These devices also include commonly bypasses, settling chambers, and other mechanisms. So when we're analyzing and looking at the efficiency of this, it's really the device as a whole that is considered in getting this treatment efficiency. Although you need to size it and decide how many cartridges you need to have in there, it's really the device as a whole. What is the purpose of this device? Well, it is used to reduce pollutants that is discharged to waters of the state, or it might be used for pre-treatment, such as for infiltration below ground. What this standard is designed for is coming up with what the total spended solids and total phosphorus removal rate that someone can take credit for with this device in Wisconsin. As far as these devices, they also can, remove metals and other pollutants. This standard did not focus on those other pollutants at this time. That is something that we may then focus on that in the future, but largely TSS and total phosphorus, especially with TMDLs, are really the two main pollutants in Wisconsin that we target with these stormwater treatment devices. Again, this device we're looking at is really the device as a whole, not just the media. There are proprietary medias out there. This standard is not meant to address that. It's really meant to address the whole system that someone was getting to put this in. As far as the standard, DNR does not give device or product approvals, per se. What we have developed here is a standard by which if the device meets the standard, you can use it. And as far as sizing the device and maintenance of it, that should be consistent with the standards criteria. So again, we don't have a list of these devices, but it is something, if these devices qualify under the criteria, they can be evaluated and utilized so long as they're following the criteria. Now, conditions where the practices apply. As I said, these are really meant for stormwater runoff. Stormwater runoff is something that, and in Wisconsin, we look at what is the annual average mass reduction of these devices. So with storm events, typically what you have, larger storm events may not have as high a treatment occurring. Smaller storm events, you get a higher level of treatment. And as you probably know, things like new development is usually striving for an 80% overall TSS reduction, where redevelopment commonly is at the 40% level, but it is judged on an annual average mass basis. This standard is meant to address that. It is not designed to give you an end of pipe effluent concentration, such as what a wastewater permit would include. Now, as far as using this standard, I mentioned new development is 80%. This standard, what we're expecting these filter devices as a credit to get for total spended solids is something that's going to range from 50 to 80% control. So trying to get that 80% new development standard, generally these devices are not expected to be used for new development as a sole device anyways. It's more likely that they're going to be used for a redevelopment site where your standard is like 40% or something lower. That way, when you have a device, yes, the device may be getting more than 40%, and what that allows for is more bypass or having sites that may have some uncontrolled areas, so that overall you can still meet that standard of 40% if it's a redevelopment site. These devices, think of them somewhat similar to an infiltration basin. They are not meant for construction site runoff. If you have a large sediment load going in there, lots of fines, you can clog them up. They are something that should be kept offline until the drainage area is stabilized from erosion. Also somewhat similar to infiltration. Now I'm not calling them an infiltration device, but they are a filter. Infiltration devices, we're filtering through native soil. One of the things with them that one needs to be aware of is when you're putting devices below ground, now you're getting down potentially into groundwater areas. These devices, at least the granular filter media, those are things that generally have dry out periods between rainfall events. And what our standard says is basically you have to have at least that granular media part of that device 1 foot above seasonal high groundwater. You also need to account for, is there backwater that could potentially be coming up into the system? It should be protected from events up to a 10-year, 24-hour event if it's being affected by downstream streams or the like that could back up into there. So, you know, putting this underground where you got high groundwater, that is something that may not work. Maybe there's an alternative that could be worked in there. Maybe you can put a under drain system around below this device to keep groundwater from getting up into there. That might be one way to try and address the seasonal high groundwater issue with them. But again, it's important, just like an infiltration device, its media needs to have dry out periods between rainfall events to aerate. Otherwise, it's likely that that media is going to have it's going to compromise that media, and it will not likely flow through there as well if it doesn't get some regular dry out periods. Okay, one of the biggest things to know with here for people designing and using these systems is there's 2 different design criteria that you need to meet with them. One is maintenance life. These filters, just like anything in life that you have, a car filter or like, if they're doing their job, they're catching pollutants. They're starting to fill up. What we have as a design maintenance criterion here is that those filters should be by design expected to last 12 months before it becomes spent. When I say spent, that is a 10% drop in flow rate from its maximum treatment flow rate, MTFR. Okay, how do you tell a 10% drop in flow rate? Well, that is something that I will get to that a little bit later. We have actually are using a New Jersey standard for making that determination. The other thing that needs to be checked is the filter flow capacity. As I said, there's systems that you may have bypasses in there. You need to look at how much of the water you need to have going through that filter to meet the standards. So that will also dictate how many filter cartridges or, you know, what capacity you have there. So again, you need to meet both of these and check both of them and use whatever indicates the higher number of filter cartridges that are necessary. Okay, as I mentioned here, now design life before maintenance. Okay, what we are using the standard is we are using a New Jersey Department of Environmental Quality certification of how much drainage area a filter cartridge can handle. As I mentioned, it's a matter of at what point is the filter cartridge considered spent. New Jersey's test is such that when the maximum treatment flow rate drops by 10% in its testing, it's then considered spent, and at that point, it should be changed. Now they're testing to get to that point. What they've come up and determined that they're looking at a 600 pounds per acre per year coming off of a surface like a parking lot is what they've deemed their test for a 12-month period. Now that 600 pounds per acre, some people have said, hey, well, that's New Jersey. Is that the same in Wisconsin? Well, actually, in fact, that is comparable to the load that comes off a Wisconsin parking lot as well. So they really were looking at the same type of load from a parking lot that's equivalent, comparable here in Wisconsin. I'll be straight up on one thing. What New Jersey's test was done on, it was actually done on synthetic particle size distribution that isn't as coarse as, let's say, the NERP particle size distribution, which is what we base our standards here on Wisconsin. So it's a little bit coarser, but this actually is the only testing where they've done this to determine when these cartridges clog up. So one could argue on one hand that, hey, it's not rigorous enough, but the reality is this is the only test right now that's available. And these devices, it is very common for them to have this certification through NJDEP.
Hi,
Now,
Eric.
again,
This is
yes.
Kate. We have a couple questions that came in. I'm
Okay.
not sure if you might remember some of the detailed background on these NJDEP calculations, but one of the questions is how large of a parking lot? And I think that refers to that TSS load.
Got it. Okay. It's parking lot, it's 600 pounds per acre for a parking lot. So if you had a 1 acre parking lot, you're looking at 600 pounds in a year. If it's a 2 acre parking lot, it would be 1,200 pounds coming off that parking lot to the filter device. And this is something that's, with this maintenance, it's actually broken down where each of these filters, they look at them, and it may be that one filter can handle, let's say, we'll make the math easy, 60 pounds of sediment before it's become considered spent. Well, being able to handle 60 pounds as compared to 600, it can handle 1/10 of an acre of drainage area for a year before it's considered spent. So that's how they do that.
Okay. There is one more question. This one maybe you want to punt down the road, but I'll read it to you and you can decide whether you're going to discuss something like this later.
Just go ahead and give them to me.
All right.
Yep.
The question is there a recommendation on how to keep a PFD offline if it's located within a storm sewer structure? For example, part of a storm system for a site.
Well, I assume you're talking about you're installing it and you are still stabilized in site and constructing in areas. These devices, you can put the structure in, but the actual filter cartridges or filter membranes, you would not put them in there. So the structure itself is fine with the sump and the concrete, everything that holds it, that you put in there. Just don't put the filter cartridges or the membranes. That is what will get clogged. So you do that after your site has become stabilized. Okay, and again, this is by design. Now, in real life, there could be more or less or unusual event that happens. So it is something that this doesn't guarantee that they don't, if there's some type of, significant load of some kind coming in there, it could compromise and reduce the life of that filter. And I'll touch upon that later with our inspections. Okay. So actually determining how many filters is needed based on maintenance is actually a very simple calculation. You'll find that our calculation for flow is much more involved. Again, we're looking at the New Jersey kind of certified approval. They actually have gone through each of the cartridges and sizes and come up with how much drainage area each cartridge can handle for 12 months before being considered spent. So here's an example. Our site is 1.1 acres is draining to that proprietary filter device system. Okay, assume that the filter cartridge has been approved by NJDEP for 0.06 acres. So if you're going to filter 1.1 acres with a device that's able to handle 0.06, the calculation is straightforward there on the screen. 1.1 divided by 0.06, it gives you 11.3. You always round up. So for maintenance, you would need at least 19 filters for this site so that it can meet the 12-month period without becoming spent by design. Okay. Moving forward. The next calculation that has to be done is for filter flow capacity. These cartridges have a given MTFR, a maximum treatment flow rate. They have limiters to keep from having more flow going through the filter than this. That is what they've been tested and proved for. If you're trying to push more water through than what they were designed to handle, they likely will not have as good of a treatment efficiency of more water going through them. So they are limited with flow restrictors or similar, so that they don't exceed this rate. As far as what affects how much maximum treatment flow rate, how many cartridges you need for flow, it's going to be based on the site pollutant removal that's needed. Are you dealing with a redevelopment standard of 40%? Do you need to hit a higher percent than that or not? Also, Wisconsin's annual rainfall, the rate at which it comes down, that distribution affects how many filters you need, and the PFD specific treatment performance. Now, the PFD specific treatment performance, what you find out, I haven't said it yet, but we are using Washington State's TAPE approved reports and devices are what we are allowing to be used. Now, Washington State, when they give an approval for a device, they have given approval that that device meets 80% TSS removal based on real stormwater runoff. One of the things that Wisconsin has that is different than just about all other states is that our standards are based on treating the NERP particle size distribution. When I say NERP, that's the National Urban Runoff Program. There was a particle size distribution that was put together, pulling particle size distributions from different areas of the nation to come up with one kind of overall distribution, which is on the smaller size than what has been found to come off of runoff sources in many areas. I will readily admit, roadway and parking lot runoff usually isn't quite this fine. But what I can say, kind of in defense of that, is when you look at the very up gradient areas, that they're usually the particle size distribution is coarser than NERP, but as you go down gradient at your regional facilities, the actual distribution can be finer than the NERP particle size distribution. And for water quality needs, we really need to have getting at trying to get to those smaller particles. The end result is Wisconsin has always used the NERP particle size distribution as its standard, and we are continuing with that approach here with this standard. You will see that we will adjust that efficiency that Washington State and the TAPE program has approved. We will take that efficiency and adjust that downward based on the NERP particle size distribution of the rainfall runoff event that was tested. Now, in coming up with determining what is the maximum flow rate needs, there's actually two different calculation processes for flow rates. The first one, option one, is the calculation process that's laid out in the standard, which I will be going through. The second option is use of an approved model. When I say use of an approved model, models like WinSlam or P8 are generally approved models. DNR has put together some conditions or restrictions through our guidance memos on how to use those to adapt them to Wisconsin. At this time, WinSlam does have two proprietary filter devices in its model. I don't believe P8 has any at this time. We have looked at that in WinSlam, and what those two devices in there and how they're done, we do approve that you can use WinSlam to model that. I am not going to go through how to use WinSlam here or looking at in there, but that is an alternative. Now, what we heard, very large and clear, one is there are other filter devices on the market. We are largely looking at those that have been approved through the Washington State TAPE program. I don't know the exact number. I'm going to say there's at least a half dozen of them that have gotten that TAPE GULD approval for sediment. They call it a basic approval. They have a number of different approvals. They have it for phosphorus. They can have it for different metals. But the end result, what we're using is those that have received the TAPE GULD approval for basic, which is sediment. And with that, we work through the process that I'm going to be going through from here. Now, the standard 1010 does have some examples in there. And I think it does a pretty good job of laying out how to go through them. So if this presentation isn't as clear and you have questions with it, I suggest going to that standard and looking through those examples in there to help work your way through it before, giving me a call. Granted, if you work through things and you still have questions or want to check with me, you are welcome to shoot me an email or give me a phone call and I'll try and help you with that. But I do think the standard goes through pretty well with the examples that are in there. The other thing, we've developed a spreadsheet calculation to help with the NERP adjusted filter efficiency. That is what I believe to be the most complex step or potentially confusing step, but our spreadsheet, I think, also makes that pretty clear to work through. Okay, now coming up with, site treatment. How much do we need to treat? It's actually a very simple looking equation. You're essentially looking at it and saying, okay, well, how much runoff is filtered times the efficiency of the filter gives you the amount of control, such as for TSS, for the site. So if you're looking at a redevelopment site, generally, or at least DNR statewide standard for redevelopment is 40% TSS control. I know there are individual municipalities that require more than that, especially to help meet their TMDL reductions that are expected of them throughout their municipality. But you need to know what is the standard you're striving for. Really, the next step in the process is, what is the overall NERP adjusted filter efficiency for the filters that I'm looking at using? And then based on that, you are going to be able to calculate and figure out what percentage of the annual average runoff that you need to filter to meet that standard. And then the amount of annual average runoff basically is used to figure out how much filter capacity, how many filters, how much maximum treatment flow rate you need to have to treat that water. Okay, as I mentioned, we are using the data from the test report from the Washington State TAPE certification. They've done a testing of real stormwater. They generally have about, I believe it's somewhere between about 12 to 15 real stormwater runoff events that were analyzed. They look at some of the particle size distribution from at least 3 influent samples. And then they analyze all of the effluent samples for those like 12 to 15 events on what the particle size breakdown is. And what we're doing is we're looking at basically how the particle size distribution compares to the NERP particle size distribution. And if it's not as fine, basically they're going to have a reduction in that rate that they had measured as part of that certified test. The other thing we have in there is we're pushing for is having at least 15 influent and effluent particle size distributions that are taken. A lot of the testing that has occurred only had 3 influent particle size distributions in there, and we're adding a safety factor. We're adjusting that rate down by up to 10% if there's less than 15 influent and effluent PFDs. Okay, I know this is pretty small. Hopefully everybody is at least looking at a stationary computer or laptop that has a big enough screen. But when I say we're looking at adjusting the NERP particle size distribution, if you look on the left column, particle size microns, generally this TAPE testing, they've had the particle size distribution broken down into at least 3 groupings, and these are the most common groupings that they have. Less than 4 microns, between 4 to 62.5, and greater than 62.5 microns. Now the next column over, NERP PSD, percent by mass, that is the percent by mass of particles in the NERP particle size distribution for that grouping. So 29% of the mass of basically TSS is smaller than 4 microns. 58% is in that middle category, and over 13% of the mass are particles over 62.5. Now in the far right column, the X and the Y, we will need to look at the report and determine what the average percent mass in those two categories is that was used in the Washington State tape testing. So we need a value for X and a value for Y. Now what we have, as I've said, we've developed a spreadsheet calculation to help with this process. And this is where now I'm going to switch over and hopefully show you a little better.
Eric, we do have one more question related to the tape listing.
Okay.
The question reads, does Washington State Tape or New Jersey DEP have a list of approved proprietary PFDs that we can select from? I did just paste the Washington list that we had kind of researched and analyzed as part of the teamwork into the chat box, but do you have anything more to add as far as that starting list?
Yeah, my recommendation would be as far as NJDEP with the maintenance, we're using that just for maintenance, but we're not, what we're using is devices that were approved for tape. So I would suggest looking at the Washington State tape approved devices. They have a website where, as I said, they've got different kinds of approved. The main approval that everyone is trying to shoot for is this gold approval. You'll also find that they have a pulled and a culled, which means kind of their initial stages of, hey, we did synthetic testing, it looks good, we're going to do real stormwater testing, and the next level is kind of checking again. But the gold is really the gold standard, you might say, where they have done their analysis. It is now available for statewide use in Washington State, and actually not just Wisconsin, but there are many states in the nation that are using that certification as what devices should be used. So I would suggest looking at what has been approved for Washington State, gold approval for basic approval. When I say basic, that's their sediment. They also have additional approvals for phosphorus and metals, and I think even bacteria. But that is where you go. Now, I do have one kind of caution in there. The device, our standard, what we're looking at is we're looking for a device to operate for 12 months by design without having maintenance or requiring by design. Now that approval in Washington State, they do have some of these other devices that I'll use a word, I'll say I'm kind of like a tree box. They're actually something that is a system running it through soil or a mixture in a smaller area, but some of those smaller, I'll call tree box or smaller designs, they aren't necessarily going to get you 12 months of operation. Some of those devices, they know that they're going to need regular maintenance. They'll probably need to have the top material cleaned out every 2, 3, 4 months in order for them to continue to function. So they have a lot more water coming to them than what they could handle for a longer period of time. So that is where to go to look at those devices, but just a caveat, like I know some of them are actually devices that are also, that won't make that 12 months maintenance. So you do have to check that part to make sure that we're looking at something that is expected to be able to be designed to go to a 12-month period without maintenance. Okay, so I think that
Thank you. So yeah, it does. One of the attendees also posted in some information about the NJDEP maintenance list and the expired devices list that aren't current on their approval.
The expired devices list, okay.
That aren't current in their, I guess, approval process with NJDEP.
Okay, that is something that I think I'll have to look at and provide a response to that on a follow-up, because I'm not fully familiar with that, so.
Okay, thank you.
Okay, well, I'm gonna now move on here again. Again, what I have up, this is a spreadsheet that I put together to help with the adjustment of the pollutant efficiency. As shown in here, the shaded areas, blue is where you will be, or a person needs to input information. There's only 6 fields to fill in. The gold is what's calculated automatically. And as I scroll down to the bottom here, what you're ultimately looking for is on the bottom here, the overall adjusted TSS filter efficiency, where it says 69% on here. So what you'll find when you go through using the tape approved reports and information, this efficiency, overall efficiency, is going to be at a minimum 80%. It could be higher than that. So as you put the overall efficiency that was determined in the report in here, I'll just go in and this is the exact same spreadsheet that is on DNR's website. If you look under our DNR stormwater post-construction standards page, where we have technical standards like wet detention ponds, infiltration basins, bioretention, we also have this standard for proprietary filter standards 1010. You will find 3 files there. You'll find the standard, you'll find the spreadsheet, and then you'll actually find a technical note that's a few pages long that goes into discussing primarily what to expect and what to be aware of with maintenance of these systems. Okay, back here, these next 2 values are actually the number of PSDs that they have been measured for the influent. So you can change those up. If you were to have 15 for both of these or more, the safety factor would be 0. There would be no adjustment. But if either of these values is less than 15, then there is somewhat of an adjustment at a maximum of 10%. And here again, when I spoke before, looking at comparing to NERP, this 23% where I have it is really your X value, your 62%, your Y value, and then the remaining here. It should always add up to 100%. If you make a mistake and put in a value that puts you over, it'll tell you you're over. If you don't put enough, well, you're going to have 79%. That's not to your advantage. You want to fill this out, and it should add up to 100%. I have gone step by step through here. If you wanted to take time and kind of verify what's done here, I also have shown where the formulas are all shown exactly how we step through this process. This spreadsheet is locked such that the only things you can change are these blue shaded cells where you need to input information. So this is something that I believe now what we have here is pretty good at walking you through and making sure that you don't get off the track, so to say. Again, as I said, I was the team lead with the standard. I put together a spreadsheet, so if you do have issues with it or find something that doesn't seem right, feel free to send me an email or a phone call and I can try and help you there. Okay, well, I'm going to move off the spreadsheet now and go back to my presentation. Okay, now this is the same slide we went over before talking about the equation. I just want to kind of touch back and say, hey, the main one thing as far as what standard to meet, if it's redevelopment 40%, the next step is determining what the overall adjusted filter efficiency is. Well, that is really what's generated out of the spreadsheet. That final value that was at the bottom of the state page, that's the overall adjusted filter efficiency. With those variables, those 2 variables, knowing what standard to meet and what the filter efficiency is, and really the amount of water coming to the filter, we can determine how much annual average runoff is needed. And we do that by using this chart. This chart, this equation will help you. I know it's kind of tough to see. What we have on the y-axis is percent of annual average runoff filtered. On the x, it's maximum overall treatment flow rate, or that MTFR. So for example, if we were to determine that through our calculations, I'll just throw it out. Let's say we need to meet that 40% TSS control standard. And we know that our proprietary filter is going to get a 60% treatment. Well, we need to get 40. Our filter gets a 60%. Based on that, we actually can allow for about 33% of the annual average runoff, either bypassing or being untreated, not going through the filter. But a key thing that's important in figuring out here is when we do the equation, and that's on the next slide, let's say we determine that we need to filter 80% of the annual average runoff. If you look on the y-axis, 80, run into that graph, we hit there, the line, and then come down to the axis, x-axis, you'll find that if we need 80% filtering of the annual average runoff, we're going to need right about 67 gallons per minute per acre. So again, at about 80, we need about 67 gallons per minute per acre. And as you can expect, as you need to capture a larger percentage, approaching 100% of the runoff, the amount of treatment flow capacity that you need goes up very quickly. You know, if you're designing and you're used to designing things like infiltration, you know that, hey, you know, we can do pretty well getting infiltration for the first, you know, certain percentage because we're getting runoff from all our small rainstorm events. But then your larger storms where you get a fair amount of flow coming in order to capture that, you need a lot more capacity. So this is kind of a unique issue. One thing I'll mention earlier, you'll find that when you are looking and you only have to treat to a lower efficiency, 40, 50, 60%, usually you don't need that many filters based on flow, but actually you'll need more filters based on maintenance. You'll have less number of filters that will clog faster if you don't have enough, versus if you start needing to treat 90% of more of the annual average runoff, when you get up in that range, it's common that you're going to need more filters to handle the flow to get there. And if you meet the flow condition, then it may be where your maintenance is met. What controls is flow when you need to treat a larger degree. Let me move on here. Here's another example that will spell that out more readily for you. And again, the standard has this type of example in there stepping you through it. In this example, we've got 1.4 acres of parking lot where 1.1 acres is treated. So we've got 0.3 acres that is untreated. It is a redevelopment site. So we need to get overall from the 1.4 acres of parking lot, we need to get 40% TSS control. Okay, assume here that we've gone through the spreadsheet calculation already and we've arrived at the filter efficiency of 60%. And the type of filter cartridge that we're going to use from a manufacturer has a maximum treatment flow rate of 10 gallons per minute. What we need to figure out here, based on this equation up above, is what is the minimum percent of annual average runoff that we need to filter in order to get to the standard we need to meet of 40% overall for TSS control. So it's 40% times 100. You're dividing that by the efficiency of the filter times the percentage of the site that's treated. So you're looking at treating 1.1 acres out of 1.4 of the parking lot. When you go through that, the value is 85%. You need to treat 85% of the annual average runoff for this example. And so 85%, I'm going to jump back here, 85% on here, moving across till we hit this line, move down to the X, you're going to find that you need about around 87 gallons per minute per acre of capacity. So now I'm going to go to the next slide. Now, like I said, just the last slide, we determined 85% of the annual runoff is needed. We looked at the graph. We determined that that graph requires us to have 87 gallons per minute of treatment flow rate per acre. But we're actually having 1.1 acres of area draining to our filters. And that 87 gallons per minute is for 1 acre. So basically we need to upscale it a bit. We need to do that 87 times 1.1 acres. We need 96 gallons per minute of treatment flow rate. And we always round up. So with our cartridges being designed to handle a maximum of 10 gallons per minute, 96 times 10 is 9.6. We round up, we need 10 filters based on flow in order to meet the standard, or in order to give us enough flow capacity so that 85% or more of the annual average runoff is filtered. So the examples I ran through, again, maintenance, we found that there were 19 filters needed in order for the filter capacity to last for 12 years by design so that it wouldn't become spent. But based on flow, we only needed 10 filters, based on its capacity again. But like I said, 10 filters is enough to handle the flow, but if you only do 10 filters, it's expected that that filter is going to clog up and will not make it for 12 months. So that's why you need to use the higher of the two, of maintenance or flow. And what I mentioned earlier is when you're looking at treatment flow rates on the lower scale of 40, 50, 60%, you're going to find that usually the maintenance, the requirement for maintenance is going to control and require more filters than flow. When you get up where you need to do a higher treatment level of, let's say 90% or more of the flow capacity, that's when the number of filters needed, it's likely that the flow capacity may need more filters than maintenance at that point. Okay, now I've gone through and that is my completed talk on how to adjust for the filter efficiency and how to do the calculation to bring it back into a site. So what I just went through there, that is all done, you know, by hand calculations or using the spreadsheet to help you with that. You do not need a model such as SLAM-P8 or something else to go through to determine how to size these devices. This standard will allow for, you know, devices that have gone through and gotten that TEEP Gold approval, so long as they're able to, you know, operate for 12 months by design without maintenance. You can take those other devices that aren't in a model like WinSlam or P8 or something else and go through this process to size them for your site. Okay, the next thing I want to touch on is total phosphorus filtration efficiency. Now, tape, we're using the same thing. It needs to be approved through Washington State's tape approval process. In Washington State, what they have is an approval where anything that gets quote unquote phosphorus approval, it is shown that it has at a minimum 50% total phosphorus removal. Okay, we, you know, although we've done this adjustment for sediment or TSS based on inert particle size distribution, we are not adjusting the values that they're determining through the Washington State certification process. So if something has been approved for phosphorus showing that it's getting 50% or more phosphorus removal, in Wisconsin, we're allowing that credit of 50% or more to be used here in Wisconsin without an adjustment. The other thing we're allowing for is devices that have basic approval, tape gold basic approval. That basic is really just for TSS for sediment. However, there's phosphorus that is particulate bound to the sediment that's captured, even though the device may not be, you know, enhanced or, you know, specifically designed to capture a higher level of total phosphorus. It still does have total phosphorus capture within there. For any device that has a tape gold approval, we are giving a 20% total phosphorus removal credit for those devices as well. So again, you can get 25% removal right across the board for a tape gold approved. If it's got a tape phosphorus removal, those devices are getting 50% or more phosphorus removal. Okay, going through design requirements as far as flow routing, this is something that, you know, the device and the chamber and everything that's in there should be controlling it. It's making sure that it prevents from having more flow going through the media cartridges or the membranes than design, and it used that by restrictors and overflows or bypasses in the process. Oil and grease pre-treatment. These filters, they can handle, you know, some amount, a little bit of oil and grease to a limited level. However, like any filters, you can overload them and basically compromise the integrity of them. Areas such as vehicle parking lots, drive-up windows, vehicle maintenance areas, or repair areas, these can have an excessive amount of hydrocarbons or oil and grease coming from them. And these are ones that should additionally have some form of pre-treatment up front. In some cases, these devices might potentially have a baffle system to work with that, or it may be that you need something out in addition to this device to pre-treat that runoff to help remove the potential excessive amount of hydrocarbons coming into it. The other thing is sediment pre-treatment. Every one of these devices pretty much has some kind of sump, so material that goes in there, the gross material, can fall to the bottom of the sump. However, the size of these chambers that are used, might not be able to handle a significant sediment load. And the best example I can think of a significant sediment load, granted, these devices aren't, the cartridges aren't to be put in until the upgrading area is stabilized from erosion. But if it's an area that's having sand applied in the winter for traction, it is possible that if you're doing winter sanding, that amount of sediment load could actually fill your chamber right up. We know of one use of this at the Dane County Airport. The first spring they looked at the device after they put it in, it was chock full of sand from sanding. There was supposed to be a device up front that was going to be used to help capture sand. The end result is that treatment train approach to try and capture sand up front, that device wasn't put in, and it just filled the filter chamber. Okay.
Eric, we do have a question on the phosphorus, so maybe cycle back to that for a moment. The question is, if TSS removal rates are reduced based on NERP particle distribution for Wisconsin, wouldn't phosphorus removal rates also be reduced?
You are correct that it is reduced, but what we looked at for this 25% total phosphorus removal, we are confident that all of these devices that have gone through the tape GULD approval, even when adjusted for NERP, they are all going to be getting at least a 50% TSS removal rate. And based on a TSS removal rate of 50%, we feel comfortable that giving 25% total phosphorus removal credit is reasonable. So yes, you're right. The lower removal doesn't capture quite as much phosphorus, but at the low end of our range of 50%, we still feel comfortable at 25% total phosphorus removal is reasonable. And that is something that, comparatively looking at sand filters or other devices that might be getting closer to like 80% removal, maybe, the same thing can be, said for them, that catching particulate bound will get you total phosphorus, and something like, let's say, a sand filter would be even capturing more than that amount of total phosphorus. Now, with that said, I can add one just for DNR's bioretention standard, or our engineered soil mixture. That is sand, but it also has compost mixed in there. The biggest thing that works against that engineered soil mixture is with compost, it does leach phosphorus. So actually the engineered soil mixture we have in there works, good for helping to get plants going in the beginning. It actually works better with the compost trapping hydrocarbons and metals. But what it is not an improvement on over just straight sand is actually capturing phosphorus, because actually with that compost in there, it can actually leach phosphorus. So the same thing I'm saying here, we can always get total phosphorus removal from like sand. Well, that's not the case when you have organics added into that mixture. Okay, I think this is the slide where I'm at now. Design requirements. First one, this seems very basic and should be obvious. Access for maintenance. Well, that is something we want to make sure, and you should be able to, hopefully by the end of this, understand a stress. It is very important to be able to access and be able to maintain all aspects of this system. It's true, all stormwater facilities will need maintenance of some kind. Some facilities like a wet detention pond, you might not have, the maintenance that you do most years might be just mowing and working, dealing with the vegetation on the sides, or making sure that the outlet structures aren't becoming clogged. You don't necessarily have to clean out the soil every year. It might not be something you have to clean up, but once every 10 or 20 years or more. That is not the case with these proprietary filter devices. it's very important to do the proper inspections, and it is generally expected that you should be cleaning and replacing these cartridges every 12 months. That is generally the sizing that they're designed for, is for a 12-month period. So anything on that structure that you need to access for maintenance, you need that. Tangenting off here a little bit, there are some facilities today that are below ground that parts of them can be accessed for maintenance, but other parts of them can't. So parts that can't be accessed for maintenance, that's something where if that part of it fails, that may mean that part of the device has to get, torn up and removed. So, on this with filters, this is something that needs regular inspections as maintenance as appropriate. So you need to make sure that is in a way where you can readily do that as necessary. Next design requirement is requirements for reporting performance predictions. That largely is the information needed to do the NERP particle size adjustment for the filter efficiency. Additionally, it may be that, with time, there may be, I guess one thing to mention here is, as I said, there's a WinSlam model that has 2 devices in there. One thing that we heard from multiple people is, hey, we want to be able to use these devices, not have to do a manual calculation. We would like to have them integrated into models and such as WinSlam. Well, the folks at PV and Associates, John Voorhees, Robert Pitt, for them themselves, trying to customize and put these in here, it's a lot of work. It takes a lot of time. They can't just turn around and do this. So one thing that was discussed in that PV and Associates has indicated that they're interested in doing is actually coming up with a generic proprietary filter device to put in there where you can input the values necessary from standard 1010 so that it can do that process. So when I showed you that spreadsheet, or at least showing, putting in how many cartridges, what is the design rate and so forth, they're looking at having that generic filter device in there so that any other filters can be put into there so that you can still analyze it through WinSlam. Now, the next question I always get is, well, when is that going to happen? Well, that is something I don't control. That is something that, they express they're interested in doing that, but I don't know how long that's going to be before that occurs. So moving on, installation. These devices are tested in Washington State under certain conditions. Your installation must be consistent with the testing that was done to determine how these devices operate and what their efficiency is. Okay, operation maintenance. Now, as I said, we're looking to install these such that they're designed to operate for 12 months without having to require maintenance. Well, that's by design. The world doesn't always work exactly how we intended it to be designed. It could be something that an event of some kind could happen, or there's actually more loading coming off of an area than what's typical. The operation of a filter might actually not operate a full 12 months. So what we have in our standard is, for the first year of normal operation, there should be quarterly inspections to checking on that filter device and its cartridges, make sure that it is operating the way it's supposed to, and that device is not showing that any of its, or the manufacturer's indicators of the cartridges becoming spent, that nothing in there is getting triggered showing that these cartridges are already having a life that has been compromised. So after that first year of normal operation with quarterly inspections, if it is clearly shown that no maintenance is needed and that filter was operating the way it should expected, there's no indicators of any issue that is going to be failing in that 12-month period, we allow for the inspections to drop back to be an annual, once every 12-month inspection. And generally when that should occur is after the spring thaw. Try to get it cleaned out after the winter. You could have winter sand, you've got a heavier load coming off in the spring from the winter runoff conditions. That is felt to be the best time to basically go in there, change those filter cartridges. And again, it is expected because these systems generally are designed to last 12 months. They usually aren't over-designed where they're expected to last 2 years or 3 years. They're generally designed to get you through 12 months before they become spent. And at that point, that is when the filters are expected to be changed. The other time you should inspect is if you become aware of an event where there's a significant sediment, oil, grease, or some other spill that could affect these devices. You should always still check them at that point as well to make sure that event has not compromised the filters. Okay, now I know I kind of touched on this again, and I'm going right back over it to stress it because it is important. These devices, unlike your wet detention pond that, it's obvious when the outlet becomes clogged and it's not draining out because the pond's full and it's not draining out, you need to do something. These devices are below ground, they're out of mind unless you intentionally go look for them. If those filter cartridges become spent, the water is going to bypass around them, and at the surface, you won't know it unless you go in there and inspect, open them up and look right in there to see what's happening. Plus, when you're doing inspections, even when you open them up, most of the time people are doing those inspections, it's not currently raining out. If you're looking at it in a dry weather condition, if the system was clogged, water's going to be bypassing. Now there are certain indicators that each type of a device, the original equipment manufacturer has a manual that specifies here's what to look for that are signs of it becoming spent. Here's how it will look, here's what's there, and here's when you need to maintain it. So if those indicators indicate you need to change the cartridges, you need to do so. However, as I stressed, by design, these devices are designed to get you through 12 months before getting spent, but they're generally not designed to go for another year. It's really at 12 months is when these cartridges should be changed out. The other thing is what we heard from some people, well, in some situations, the drainage area wasn't all going through here. There really was no activity going on in this area. This source and load going to it was nothing near what it was intended. We think these filters can last longer. Well, if it's very clear that the equipment manufacturers replacement indicators show no sign of requiring replacement and doesn't even look close to needing replacement, then we have an allowance of, okay, go ahead, you can go a maximum of 24 months before you have to change those filters. But regardless of what the O&M replacement indicators suggest, we feel that at 12-month point, you should still be changing those cartridges out, just in case. The indicators aren't necessarily, in all cases, 100% foolproof. They are good indicators, but at the same time, at 12 months, we think they should be changed out no matter what. Giving you another idea of these granular cartridges, what usually happens is these cartridges, you pull them out. Generally what they do is tip and dump the cartridge media right into the bottom of the sump, take that cartridge, send it back to it to be recycled, reloaded over again, and they have a new cartridge that they bring with them and they put that in there. And then after they get done changing those cartridges, it's standard then to vacuum out the bottom of the sump after they basically dump the media in there. So really that cleaning the sump generally should go hand in hand with media cartridge changing. Again, usually they'll dump it right in there and then vector it out after they're done, and then you're good for until next spring again, hopefully. So with that, that's the end of my presentation. So if we have any more questions, I'll go over them.
There are quite a few. I was sort of pushing them to the end now because I did want to give you a chance to go through your slides. In the interest of time, I guess it's already 11:06, so I do want to respect our attendees' time. Are you able and willing to stay on a little bit longer and answer some of these questions, or do you want to maybe respond afterwards?
No, why don't you just, why don't you just read a question to me and I'll try and answer it as best I can and move through them to the extent we can. So
okay. I think some of these you've already answered in the course of your presentation too, so hopefully we can just quickly go through. So there's a question that says, we have a new facility with a bioretention pond next to the parking lot. Will the pond handle the load of the filtration, or will it still have an independent filtration system?
Can you repeat that again?
Yeah, this is, it's more of a design question than related to this technical standard, I think. It says, we have a new facility with a bioretention pond next to the parking lot. Will the pond handle the load of the filtration, or would it still have an independent filtration system?
Okay, now I'm understanding. The bioretention system, that engineered soil media on top of it, that is considered the filter layer that protects basically, if that system also infiltrates below there, that top layer is your filter. So you do not need a proprietary filter device to route water through before you go to a bioretention. A bioretention in and of itself is a standalone device. So no, to me, I don't foresee a reason to ever have the same water treated by both a proprietary filter device and a bioretention device. Those, I believe, are you wouldn't use them redundant. You could potentially have a site where you use bioretention for one part of a site and a filter device for another, but in my mind, I don't see ever having the same water treated by both those devices. Next question.
Okay. How do you determine your total site reduction if the filters were part of a treatment train, i.e. upstream of an infiltration basin?
Good question. The end result is the approach that I gave through the standard of calculating it. That is really a calculation process just for that treating device. It doesn't account for a treatment train approach. That is something when you get into models like P8 or WinSlam, they do have that ability to model in series. We don't have that through our manual process. That is something that a consulting engineer going through this will have to look at that and try and make the determination. So I would say that takes more discussion. If you have a site-specific example and you want to talk to me by phone and discuss it more in detail, I can do that with you, but I don't think I'm going to be able to go through that discussion here right now. Next question.
Okay. There is actually an add-on to that might provide more information. Would using the other device in WinSlam be acceptable to account for the spreadsheet calc?
Potentially, I got to look at that closer. When our team, we talked about it in the right kind of situation, potentially, yes. There was some concerns with just using that other control device straight up. So I think that's a case-by-case discussion to talk about how that's going to affect and work together. So yes, call me on that one later. I'll have to look more into there, but I think there may be some sideboard issues along with just running with that. So, okay. Next question.
Okay. It says, does winter street salt runoff affect the performance of filter media?
That would actually probably be to give the best answer, asking the manufacturers of that. That is something that has not come up with an issue of just sand. Just road salt going through it as being something that is going to render that device unusable or affected in that way. Now, our bioretention systems, what we ran into issues with there years back, some of you maybe remember, is we had soil, sandy loam or loamy sand mixed in with it with the original engineered soil mixture, and we had people just taking what topsoil was available, and they were getting some of our clays mixed into the engineered soil. And when we had road salt along with the clay, it was actually creating a kind of a seal and permeable barrier that they refer to as a SAR effect that actually, actually sealed up that layer. That is something that I do not expect to happen with the medias that are being designed. That is something that I think they've looked at, does salt running through here adversely impact that filter system? I think they can still work. With that said, it is something that our replacement period is expected to be immediately after the spring melt really is the best time to change those devices. So if that winter period had some kind of effect on them, we are looking to have new cartridges put in at that point. Okay, next question.
Okay. Considering the amount of bypass flow, can PFDs be used as pretreatment upstream of infiltration and detention, or should PFDs be used downstream of detention?
Okay, I should have maybe stressed on this better. Generally, if you've got enough room at the surface to put in, your wet ponds or bioretentions or things like that, that generally is the more cost-effective option to go with. Generally, you don't have these proprietary filtration devices putting in series with a pond or bioretention. It's kind of redundant treatment. You don't need to have one treating before the other. Where these proprietary filter devices are primarily expected to be used is on sites where the availability of land is at a premium. They don't have room to put in bioretention or wet pond or other things at the surface, and they want to go below ground with it. These proprietary filtration devices are something that, although when you look at them to start with, the capital cost might seem, hey, this isn't all that far from what it might be when I look at some of the other things. You factor in the operation and maintenance that's needed over the life of that device. What's generally expected is these proprietary filter devices are going to cost more than your surface devices. And as well, that maintenance, it costs more, and you need to remember and you need to deal with that maintenance on a regular basis. So I don't see them being used really in a treatment train unless you don't have room for surface treatment. It's really where you need to go below ground to get that treatment. Or potentially, now we don't see it often. We've had certain cases where someone has a new development, lands at a premium. They're looking to do infiltration below ground. They need to do pre-treatment before they have that infiltration. These devices can be used to help provide pre-treatment for underground infiltration because, for them, they're looking to have everything underground. Well, these devices are designed to go below ground and can be used to help satisfy pre-treatment for infiltration. Okay, next question.
All right. Is inspection of below ground PFD systems considered confined space entry subject to OSHA requirements?
I think there's a good chance that it is. That is something that you should be looking at your equipment manufacturer's safety, requirements for doing that. So it may be some of them might not, but certainly below ground structures are always something you need to keep that in mind and follow the protocols in your manufacturer's guidance for how to do maintenance of them. Next question.
Thank you. I think there's just one more. This is more of a appeal. You mentioned the WinSlam input process. The comment is, I am concerned that standard 1010 will not be used unless we get the WinSlam module you described. Given the emphasis DNR places on using WinSlam, it seems appropriate for the agency to take a role on pushing this forward in a timely manner.
Okay, well, I think I've already addressed that issue. As I said, PV & Associates has indicated that they intend to do this. the state doesn't control that. That's a proprietary model. It is something that I will again be following up with PV and Associates and checking on that to see where that is in their process and where it is in their priority of things. So that's all I can do to try and help encourage that along. Any other questions?
Okay, no, I think that's all I see in the chat box. Thank you for taking all the extra time to stick around and answer these questions.
Okay, great. Well, thank you everybody for listening in. And as I said, you know, if you end up evaluating one of these devices in that, at DNR, you can certainly contact your local stormwater specialist or engineer, but there's a very good chance that they might, at least in these beginning few years, they might be directing them to me. So if you want to call me directly or send an email, feel free to do so.
Well, thanks, Eric.
Okay, thanks everyone.
And thanks, Kate, for helping out with that. We're losing people quickly, but I did send out, again, the links for signing up for your PDH, if you can fill out that form, and to join the SOC listserv, and a short evaluation, a very short evaluation. So I think everyone's running away. Thanks for joining us. That was interesting, Eric. And if you have any questions about the webinar, you can always reach out to me on the email address that you received the confirmation on. Everyone have a good day. I think we're going to sign off. Thanks, Eric.
Okay, thanks,
Thank you so much.
Penny and Kate.
Yep, thank you.
Thank
Bye-bye.
you. Bye-bye.